All right, let me do the beginning. Thanks for joining our session today. I'm very happy that at the last moment on Monday, we got legal approval by our customer Interven. And so we have Karina with us, who's basically presenting the rest of the presentation. I'm really happy to have her here. Karina, can you go to the next slide? I'm just setting the stage here. So what are you going to see in the next 15 minutes? We talk about glycan structures, which is basically sugars that are connected covalently, so like in chemistry and linked with each other. And you see some examples there on the right side, these little trees there. So basically, yeah, they are graphs. And the glycan composition, so you see the colors and the shapes of the different sugar monomers are connected to each other in a tree-like structure. And depending on the composition and the length of these sugar trees, they are disease specific, for example, for Alzheimer's disease or for cancer. And that makes them really interesting to study them in terms of targets. And Karina, if you go one slide back, we got the problem that the methodology of measuring that in the lab is not really 100% accurate, and that need some more technical, let's say, supporting material. And because we have kind of pattern matching problem and in a graph, it makes us a very, very cool use case for graph technology. And so on the lower one, you see like sometimes we cannot see what's in between this molecule there with these question marks, so we don't know how long the sugar tree is. And then on the right side, you see just a mirror image. Sometimes we don't know the orientation of the monomer sugar molecule. Now, Karina, go to the next slide. That brings me to basically the first conversation that I had with Karina, and we draw kind of a little whiteboard session here, how we can do that in Neo4j and using that with variable length queries. And so this is basically the handover to Karina, and she will explain you how far they get so far. So Karina, stage is yours.
Yes, thank you, Alex. That's very kind introduction. So I'm very happy actually to be here today sharing a little bit of what we do at Intervene. I'm a clinical data scientist in the company, and as Alex mentioned, we start discussing about how to collaborate with Neo4j when we wanted to analyze these three structures or glycans. But let me start to explain a little bit what we do. So we have heard about proteins, and these proteins, to be functional, they need to have around these sugars that Alex were mentioning. And in the cool picture at the right, you can see them in blue, right? So they are attached to the surface of the proteins. We call them saccharides or glycans or sugars. And when they are attached to the protein is able to do its job. What happens if you think about in one single protein is that you could have different glycosylation sites. And that means that the glycans are arriving there, they are attaching there. Sometimes you have them, sometimes we don't have them. But we have per protein, we could have, let's say, 10 different possible sites. 3 sites. And for these 3 sites, we could have like 10 or 5 or like different possibilities for glycans to be attached in there. So the complexity starts increasing because instead of looking only into one single protein, now we have to look into the same protein, consider that it has 3 sites where these sugars are arriving. And then if we consider that we have 10 possibilities, then we will end up with 1,000 glycoforms of that single protein. So when you think about how we have been analyzing disease, at the beginning we started with the genome, then that increased to the transcriptome. When we moved to the proteome, we were already analyzing 1 million of proteins. But now when we look into the glycoforms, we are in a really, really complex level of analysis, because the detail just went a little bit higher. And it's very interesting because we know already that like some proteins are playing a really important role in different diseases, but it might be more about the sugars that are attached to these proteins, and not only the single protein as an entity. So how we do this in an intervene, as Alex was mentioning already, is not an easy process. What we work with is blood samples from patients, and we analyze the serum or the plasma in these blood samples. And they go into methods that are liquid chromatography and mass spectrometry. And this is helping us to quantify the abundance of those glycopeptides. And by glycopeptides, I'm referring to the sugar or the saccharide attached to that site into the protein. So that's what we are quantifying. And this is after these methods, this goes inside to a software that was developed in-house by Intervene, and it is pretty much where all of our AI technology is applied. Because from liquid chromatography and mass spectrometry, we obtain the spectra, and this process used to be done in the past manually. Now with PIP, that is our platform, this is performed in some seconds. So it reduces the work in something. That's something that used to be done in months, now in something that it could be done in minutes. So this allows us to, instead of looking again into the proteins, we can go that level deeper. And once that we have this information about the glycopeptides in each sample of each person that is enrolled in the study, we are able to create models. We could do classifiers for, do diagnostics for a disease in particular. We could also kind of determine if a patient is going to be or is going to respond a specific drug. We could analyze it. It doesn't have to be, we mentioned that this is about cancer, but it doesn't have to be precisely cancer. It could be another condition. And this is really important in terms of what we could do in the future if we extend this technology a little bit further. Because once that we have the information, once that we have the model, well, we are reducing that list of thousands of glycopeptides probably into a list of 20 that are representing, or that are the markers for a disease, right? And that is where the challenge arrives, because now that we have this small list of markers, then we have to look into the other information that we have about it, that it will be like the publications, the interactions with other proteins, all the information that we have about pathways, and the glycans, as Alex was saying before, the structure that they have and how this is impacting the behavior of the protein itself. So pretty much in the diagram that you have in here, it's our workflow inside the company. And this is, if you think about it, we could translate it already to how it looks into the graph, because we have the data from patients. So we have information about age, ethnicity, probably exercise. It depends, as you might imagine, per hospital and provider, the information that they give to us. But also we have that information that becomes some of the notes. Then we have different notes for the samples, because one patient could provide us more than one sample in different times. And then when we start analyzing these samples and they go through all the methods that I just explained, it becomes more notes, and then we analyze these samples, and then we get our study notes, and that's how we just start growing and growing the graph. So at the beginning, our idea for working with Neo4j was only focusing in the structures of the glycans because they are naturally a graph. But actually, we have expanded all the data that we have. Instead of looking into a normal database, we are already implementing all this data as a graph database. This is the overall, the general schema. You could see, like in the red part at the left, we have all the samples of graph. Then we go to the glycopeptides. This is linked to the protein-protein interaction subgraph. We have also the glycans of graph, and then we have the yellow beautiful part that is at the right. That is actually how the glycans are drawn. And at the middle, I left the purple part that is the reference. All the publications that we have could include publications or trials or studies that have been done in terms of the proteins and glycans that we are analyzing. This is not all the data that we are using, of course, is produced in-house. We are integrating other databases into our database, of course, like reshaping the data in a way that we could access easily. And these are some of the other databases that we are integrating to ours. And there are a lot of libraries for Python and Neo4j, but actually a lot of the study that we do inside Intervene from the clinical data science team is done in R. So for me, R is my everyday nowadays, and actually it's been very easy to get all the data that we have from the department, what we produce in house. Also considering all the data that comes from different databases, do data cleaning, some data formatting, writing the queries in R to produce TXT files, and then upload them into Neo4j. So I think that it's I don't know if someone else could come in the future with a better response for this, but so far this has been the pipeline that we have adopted. It has worked pretty okay, and I wanted to share with you actually how we're doing all this integration. And well, I will show you a little bit of just some examples. And imagine that you have a protein, and we have a hemo. Here is the abbreviation for this protein, and what is on the screen is Bloom. Some of you might heard that Neo4j offers Bloom and also offers the browser. This is a safe query inside Bloom, and practically what it's showing is, for hemo, that is the protein in blue, is showing what glycopeptide was identified as part of some of the studies that we have in-house, and which glycan was identified in there, and which are downregulators, or the first downregulator for this protein in particular. And then we could access also to the publication. This is a very simple schema, but it has some restrictions for you to see how easy it could be to show to someone else just by clicking or providing one name and clicking on it, just the result of different information that we already have in-house. If we go to an example for the browser, this will be a little bit different. That's how actually the browser output looks. And there is, in terms of the glycan, that is these structures, it's a world. I have to say that also when I came into the Glycoscience world, I was amazed by the amount of information that is in there, and there is a lot of publication. It's very easy to get lost when you are analyzing a protein. Then you get a glycan, then you want to know more. You have to access different databases, and it's complicated. And what I have found in here is like actually just if I want to look for publications that are specifically for my saccharides, and you can see here in the query, just giving the date, I will just pop them immediately. And if I want to put some conditions to this sugar, to this saccharide, I could provide more, and I will get this information like in less than 10 seconds. So I have found pretty useful, and we can do more queries, a little bit more complicated if we want to get a little bit more information. Um, and you can see, I think that for people like me, that sometimes we like to have the queries and the codes and get the outputs straightforward, but we also like to have this visualization that actually allows you to see patterns. This is a really very useful tool. I have enjoyed it, I have to say. I've been enjoying my journey with Neo4j. I really we're looking forward to what we could do in the future and keep growing. At the moment, we are integrating more data from other databases. We are also producing more data to grow our in-house database with more examples. You could imagine that every time that we do an study, we have thousands of patients, and that all that information about the abundances of the glycoproteins in these patients goes straight to our database, and that allowed us to actually discover patterns in terms of disease and behavior. So this is what we do, and yeah, with that I will say thank you. And Alex and I think we are gonna take questions if there is some time.
Superb. Thank you very much, Karina. Super interesting project. I really like it. And I feel like you. I mean, I used to be a customer, so our highly connected data is probably the best kept in Neo4j. Yeah, it makes sense. I answered some questions already in the chat. If there are any other questions, let us know here or in the Q&A. So we will be there. And thanks again for Karina from Melbourne. So it's very late in the evening already. Thank you so much. And yeah, hope to hear from you more. And let's all hope that we can get some cool diagnosis or treatments for cancer or any other widespread disease. Yeah, with Interven. Thank you very much.
Thank you. You are mute.
Karina, thank you very much for participating. Very nice presentation. Really loved it. And,
you know what? My nose is running, so I got really distracted. But I don't know if it's the high fever. So
okay.
sorry.
We are still online, class
It's
says.
okay.
Get well soon. Take a rest, and yeah.
Yeah.
We'll talk to each other soon, and I will stay here in the chat and answer some questions.
I
And you
can
enjoy your
answer
evening.
some questions if you want me to. Like at least this one that I have here. It says,
Oh, it's
"Do
still the
you have?"
question time probably.
Yeah.
Okay. Is there a specific question still online? I don't see specific questions. So Ivana earlier asked if you are storing each patient as a single patient and then to it the glyco patterns, or are you storing that in terms of groups, like a patient group, like I don't know.
No. It's everything is
Individuals, right?
stored by patient and by sample.
I see.
So the abundance of glycoproteins in each of the patients vary by sex, by age.
Yeah.
So that's why it's very important to keep tracking per patient of the concentration. So everything is safe individually. Yeah.
Okay. Cool.
Yeah.
Cool.
And also for the quality papers, they are, most of them we are taking them from PubMed. So we try to keep also the journal, right, in the journal in the abstract. That's a great area because I mean there is we tend to go always for publications in Nature, right?
I often get the question, Karina, in other perspectives, like how do you see the quality of the paper? Well, my answer is I'm not the judging person, right? We integrate and to a certain extent we trust the science, even if it's, I mean, even if it's in a high-ranking journal, it can be wrong, right? We sometimes measure artifacts and then you cannot really say because it's a high-ranking journal, it's more right than others, or we trust that more. I would see that rather being neutral and take a step back, integrate the data that we can get, and then have other kinds of data sources proving or disproving that this and that fact, or even have in the database. I see that often with customers having like both. Let's say if there are two scientists that have contrary approaches, to have them transparent in the database, and you can basically query both sides and say, okay, I'm trusting this more, or this experimental data supports more the other research.
Yeah, there is in terms of when we are working with data from the lab, and even when I remember when I was doing my PhD, it's the same problem because there is a lot of good publications actually in not high impact papers or journals, and there are like really high quality journals that actually accept sometimes publications that are not that good or not reproducible, at least in the lab. So it's hard to measure, and it's as you were saying, is like let's just collect it and actually like keep record of journal and everything, all the information about the publication, and then to decide if you have only one publication, probably from one regulation between proteins, and no one else have noticed ever that relationship between these two proteins. You might have some questions, probably, but what happens if never anyone else gave it a chance, and actually the relationship it is in there is just like no one has noticed. So it's a good way of discovering also, like if you think into pathways and networks in protein interaction, right, and you see that there is always a connection or maybe different paths between two proteins, and there is one paper that is telling you that they have observed actually the direct link, you might consider it again because you might have other paths between those two proteins that are already showing you the relation. So yeah, I'll say that let's just give a chance to.
Totally agree with that. We also have a white paper with Novartis, and they integrated lots of data, and they gave it a confidence level. So they basically count the number of occurrences between two nodes and the relationship, keeping like a confidence level and saying rather of relying to an impact factor or to a high-ranking journal, saying rather how many times do I see that in my huge literature data set, and does that give me more confidence? But even then, you know, like there can be new methods after decades, right, that can prove or disprove things. So I would keep it rather transparent there.
Yeah.
All right. Good point that a knowledge graph can also help with cross-validation or discover positive or outliers. Exactly.
Yeah.
And especially we see that with cross diseases. So sometimes we have people that are studying only cancer and they're very cancer focused, and they never saw that the same gene is also related to diabetes type 2. And then all of a sudden you have kind of comorbidities that kind of grow. And so you have new information coming to that, and this would kind of be like the disproof, right? Do you erase the cancer relationships to this protein because you have new ones in diabetes, or the other way around? Or would you keep them both? But maybe it makes sense scientifically or in the mode of action. Yes.
Yeah, exactly.
All right. Any other questions? Thanks for this very active Q&A here. I see some super engaged people like Peter and Ivana. Really cool.
I will write my email. I think that I haven't provided my email, but let me. Where can I share this? I have it in here. Well, I will type it as a question just because I have a.
Yes.
Yeah. Okay.
Very cool.
Yeah, so that's my email. So feel free to contact me if you have more questions or anything. But yeah, I'm very excited what we could do, and there is. I mean, there are a lot of things that when you find them, they seem obvious, but they weren't until
They
you
weren't.
see they weren't, right? So
Exactly.
it happens to me. I love graphs, but every time I do a query and it's like, oh really? This is connecting this way,
Yeah.
and you notice like, even if you are the designer of the graph, once that you see it it takes it's different, and it's a good way of exploring data, finding holes in the data, because sometimes it's the opposite. It's like that some things should be connected and then they are not, and there is no way to find those gaps
Yeah.
until you visualize them. So yeah, I'm very keen, and if there is no more.
I think not. And I don't know if we will be kicked out here at this session, because Siddhant said that the last session is already starting. So I would say write us an email, and we're happy to take other questions via email, or just get in touch with us. Thank you very much, and bye bye.
Hello, everybody. Welcome to this talk on building graphs with nodestream. My name is Zach Probst. I'm a senior software engineer in Intuit's platform security team. Super excited to be doing nodes again. I was here last year and it was a ton of fun. So I'm glad to be back and doing some more graph stuff with you all. So let me go ahead and get started. Outline what we're going to be talking about today. We're going to be talking about the love-hate relationships graphs have with data, and how data is messy, and graphs help kind of clean that up, and all the challenges with doing that. And then we're gonna go into what nodestream is and what it solves for, and why you might want to use it. And then really my objective is we're going to spend most of the time just building a basic little graph app with nodestream. Get a feel for what it's like, what it does for you, all the complexity that it takes off your shoulders, and just getting started with building. We're all here because we love graphs. Graphs are cool because they help you relate data together and kind of cleanly structure it for you. But the reality of the situation is that data is like a mess. There's all kinds of data that is mistyped. There's data that's encoded in weird ways. There's data that doesn't make sense, that's ambiguous. And it's hard to process data like that and make value out of it. And as you do it more and more, you find that you keep reaching for like the same bag of tricks. You keep doing the same things over and over again in like slightly different ways. And all the time you spend doing that isn't really adding value. You're solved problems. And it would just be a lot better if all of that was kind of wrapped up in a toolkit for you, so that you could build pipelines without really having to worry about little annoying things that get in your way, like ambiguous variables or escaped JSON strings inside of other JSON. Crazy stuff like this is stuff that we found in our wild environment, and we decided to try to clean that up and process it into a graph. And nodestream is sort of the result of that. So What is nodestream? Well, first and foremost, it is now open source. When I was here last year, we were still building this internally. It's been in development for maybe about a year and a half now in various different forms. And at its heart, what it is ETL for your graph databases. And it tries to be as declarative as possible and take as much responsibility of coding random things out and away from you. So it's a YAML-based DSL or domain-specific language that is for pipelining data into your graph database. It tries to do all kinds of things handy for you. For instance, it'll try to automatically index and add constraints to your database to improve its performance. It'll automatically export a GraphQL schema for you. We'll show that at the end. It has all kinds of optimizations baked in. It's really designed to do things as efficiently as possible. And then since we've open sourced it, we've also been adding a plugin ecosystem around it that do handy things for you, like sourcing .env files and adding extra controls. If we have some time, I'll show you some of that at the end. But the real idea behind the plugins is that you can add extra behavior to nodestream automatically, frictionlessly. That's not part of the core framework, but for your specific use case, you might need, depending on what systems you're integrating with or how your project is going to be deployed, those kinds of things. But we're going to see all that kind of live. So how are we going to do that? Well, imagine, like, for instance, we're a scout for a soccer team. We want to analyze potential players we might want to sign for our team. We want to do some analysis on what clubs top players are playing for, what countries they're coming from, figure out maybe where we're going to build a scouting network, those kinds of things. And so we want to ingest data about players and teams and what countries people come from and stuff. We're going to pull that in from a CSV file in this case. And then hopefully we're going to build an API out of this data to access for our analysis. So let's go ahead and start building. I'm going to exit the slideshow and we're going to pop over to a terminal and start doing things. Actually, before I'm going to do that, I'm going to quickly show you the nodestream GitHub repo. Like I said, this is open source. I invite you to check out the code and check out all the features that are available. And you'll see that in the installation, it's real simple to install it. You just pip install nodestream. Nodestream is all built on Python, so it should be accessible to developers and data scientists alike. And like I said, just pip install it. And what you'll get out of it is a CLI. So if you type in nodestream list, you'll get a series of commands that you can execute. We're going to go ahead and run nodestream new, which is the command to generate a new project. I'm going to call this project players, obviously name it better than I am, and hit enter. It's going to take a second. It's going to pull down a template and generate a project for you. You'll then be able to enter a player's directory. And I'm going to open this in my editor of choice, which is VS Code. You can use whatever you like. And I'm going to just walk you through some of the basic files that are part of this project. So first and foremost, you have this nodestream.yaml file. This is sort of your project. This is where you're going to store all of your references to your pipelines, as well as some configuration about how to initialize those pipelines and a handful of other things as well. Next to that is a pyproject.toml file. If you're not familiar with Poetry, Poetry is a dependency manager for Python, kind of like NPM or Maven is in Node and Java, respectively. So this is already wired up for a nodestream project and includes nodestream as a dependency. You can go and add extra dependencies and all the things you might like to do. The README is basically walking you through the same things I'm walking you through. So there's links in here and some basic information as well. So the next thing is there's this folder called players. This folder in your project will be named whatever you named your project. And it's actually a Python package. Everything about nodestream is extensible and pluggable. So you can add extra behaviors. And the idea behind it is that the framework isn't meant to kind of constrain what you do. It's meant to just guide how you structure your applications and how you ingest data. So there's all kinds of things that you can add to your project here. So you can drop to Python to do something custom whenever you might need. That's going to be out of the scope for this a little bit. So I'm just going to go ahead and collapse this folder. And we're really going to spend most of our time in this pipelines folder, where you'll see there is a sample YAML file. This sample pipeline might look a little weird at first, but it's pretty straightforward. What it's doing is it's counting through all the numbers in the range up to 100,000 and creating a node in the database called number for that number. So let's just go ahead and see how that works. In the backend, I have a Docker container running Neo4j already. You can run this through Neo4j desktop or connect to a remote instance on Aura or whatever. But I've already just got one running locally here. So let's run that sample pipeline and just kind of see what happens. So if I run nodestream run, and then the name of that pipeline again was sample, so I'll just type in sample here and hit enter. It's going to think for a couple seconds, going to read that file, and then start loading data into the graph. And it's updating you on its progress as it goes along. And in a second here, once it's finished, it's going to print out a summary of what it did. So it decided to create a key on one field, decided to index another, and then it decided to add 100,000 nodes to the database in just a few seconds. So if I go back to my browser, in the tab here, I have loaded up a Neo4j browser window. If I just refresh this real quick, you'll see that we have number nodes and we have 100,000 of them. And we can see what they look like. If I just click on one of them here in the sample, I picked on 15 here. You see that 15 was added as a property. And then you'll see that there's a few other properties here. This is one of our team's favorite features about nodestream, is that it attributes how data gets added into the database and at what time. So it'll have a timestamp for when a node was last updated overall, a timestamp when a node was last updated by a particular pipeline, and then a flag for the fact that that node was ingested by a particular pipeline. So as you have data that comes from multiple different sources and you're looking at your database wondering, how did this even come to be? Where does this come from? You have kind of built-in attribution on where your data is coming from based off of those pipeline names. So that's pretty handy. As much as I like counting numbers, it's not particularly interesting. You know, I'm a scout for a soccer team, so let's get some player data in here and do some player scouting. So I'm going to go back to my terminal real quick because we need some data. I'm going to create a directory inside of my project called data. You can name this whatever you want. And I'm going to copy in some player data from the FIFA video game to use as an example. And I will go back to my editor and I will show you that data file. So there's a handful of properties in here. There's a player ID, name, nationality, all these kinds of things. We want to process this file and create nodes and relationships out of these people. And I flashed on the screen before we left kind of our objective schema that we're going to go for. So let's build this out piece by piece. And we're going to start with the player node. What we're kind of processing here are players, and we're relating them to other things. So this player node is what we refer to as the source node. So just keep that in mind for a second. But before we do any of that, we need to start loading up this file and processing it. So I'm going to go into my pipelines folder, and I'm going to create a pipeline. I'm going to call it players.yaml. And if we refer back to the sample real quick, just to show you, again, this is just a set of steps. We're going to create our own set of steps that's similar to this. So I'm going to refer back to this sample pipeline and just show you how this pipeline came to be as we build out this player one. We're not counting numbers. We're trying to load a CSV file. So if I consult the nodestream documentation, there's a feature in here called file extractor. Take a look at that. And I'm going to copy this YAML blob. Basically, this says, hey, we can load files from different file formats. Let me copy this blob and walk you through it. Like I said, a pipeline file is just a series of steps. This first step is the file extractor. This implementation keyword here means this is the Python package or module that you should find this class in. And I want you to load up an instance of this and pass it these arguments. That's all this YAML file is really doing. So I'm going to go ahead and replace these sample globs with a reference to data/star.csv. So I'm going to say, hey, load up every CSV file in the data directory that I just created, which is just the one file that I had from before. Now let's go ahead and get into the second step. The second step is what nodestream calls the interpreter. The interpreter is responsible for mapping like the raw data, each individual record from that CSV file, into the nodes and relationships. So let me copy this block and we'll get started with that. So interpretations, the source node, remember I talked about the fact that what we're really ingesting here is different players. So this is what nodestream will call the source node, and then we relate to other nodes. So if we're doing that here, we want to change this node type from a number to a player. And then we want to say the key. Well, what's the key for a player? How can we uniquely identify a player? Turns out this data has a player ID field, so we're going to use that. So I'm just going to copy this player_ID text. And you'll see here that it's got this left and right hand side mapping. The left hand side is what we want the property to be called in the database. So we'll call this ID. And then the right hand side, you'll see it says James path, and then in this case it says index. Nodestream works sort of as if everything was cast to JSON data. So it will load CSV data and sort of map it as the equivalent in JSON. You can load JSON data and do all kinds of crazy stuff with nested JSON queries. But since we have a CSV file, it's sort of inherently flat. So I'm just going to go ahead and put this player ID here for the right-hand side. And we're instructing that every player node has a key that's named ID. And the value of that key is this James path, whatever's on the resultant end of this James path query. Let's see how that works just to visualize it. But before we do that, we just need to grab one last step from our sample pipeline, which is the instruction to write to our local database. So I'm going to go ahead and copy paste that in. And I'm so excited, I'm going to run my new pipeline. I'm going to type nodestream run players, and it's going to blow up. And it's going to say, hey, there's no pipeline with that name. You can check out what pipelines are in your project by running nodestream show. That's going to spit out a different table, and it's only got the one pipeline in it, even though we created a new pipeline. What the heck? We have to go back to our project file and add a reference to it inside of our pipeline section of our nodestream.yaml. So let me quickly do that. I'll say pipeline/players.yaml. And then I will save that, and I'll go back to the CLI. I'll run nodestream show again, and I'll confirm, heck, there we go. We got our new players pipeline. So let me try to run that the same way we ran the first one. Run that. And if I didn't mess anything up, it'll say, look, I'm already done. Decided to index one field. I decided to create one key. And then I upserted 100 nodes into the database. Again, let's confirm, make sure it's in the database. Look, we've got our new player label. I click that guy. And we've got players. And they've got this ID field. That's good, but not particularly useful. So let's go ahead and complete out the rest of the schema. We'll add these properties and relate it to these nodes real quick. Most of this I've just been copying, pasting, and working off of memory. Again, I'd like to point out everything's documented. So all these interpretations that we're working on, you can see all the properties here and what they do, so you can quickly do this yourself. Let me go back to the editor for this pipeline. And I'm going to add in a new instruction for our properties. And this takes a map very similarly to how we took our key value for our player node. And it's a map of, again, the left-hand side with the properties, what the property will be named in the database, and the right-hand side of how to get at that value from the data. So if we refer back to our CSV file, we want to add name, age, and overall, which is a rating. So I will do that. Name, we'll call that to name. Age names path is age. And then I don't like the name overall here. I don't think that's particularly useful. I'm going to call this rating. And that is going to be mapped to the overall thing here. Just so you know, these don't have to be named the same thing. But this is a graph database. After all, what would a graph database be if it didn't have relationships? We want to relate to the club and the country. So let's go ahead and do that. There's a relationship instruction for that. In the relationship, if you think about what it takes to build the relationship, we need to know what we're going to call this relationship type. We need to know what we're going to call this node and what the key for that other node is. And that's basically all we're going to provide to nodestream here. So we'll say relationship type. Let's do the club first. So the relationship between a player and a club is that they play for it. So we'll do plays for. And the node type we said was going to be the club. And the key to that node. If we look at the data, we don't have anything better than the team's name. You'll see here FC Barcelona. So we're just going to use that as the key. So we'll say name here, and then we will say that that is team. And if we look super close at this data, it's got this weird little quirk in it. The data has this trailing space for some reason. I'm not really sure why. It's just how this data came to be. This is the kind of stuff we'd like to clean up before we put it in a graph database. So we're going to go ahead and do that. Nodestream has a feature called normalization and normalizers. So normalizers do little basic transformations. You can see the examples here. So I'm going to copy this trim whitespace one, and we're going to add this to a section called key normalization. And we'll do that. And we'll do our last relationship then, which is our player to country relationship that we've called originates from. Originates from. The node type is country. And the node key. Again, we have just a name for this country, which is named nationality in our data. So we'll go ahead and grab this. And this doesn't have the same quirk. The nationality is normal. We don't have to trim off any white space or anything crazy like that. So we're not going to add the key normalization section. And we're done. So we've made our changes. I'll save them to our file. Just rerun our pipeline. And we'll see that it's done a whole bunch of other things. It's indexed extra fields. It's created new keys in the database. And it's upserted more nodes and created 200 relationships, which is kind of what we expect. If there's 100 players and there should be 2 relationships per player, we should see 200 relationships. Let's quickly verify our data. If I refresh this, click on players, we see now they have their name and their rating and their age. If we double click on them, you'll see that the relationships start coming to life. Here's Argentina for the country. We find a relationship between players. We have our club that players are playing for. We see here's a bunch of the same teammates. And we've got our data. Now we can go and start doing all kinds of analysis. But before we do that, we really need to expose this information via an API so that we can build a front end around it or something like that. But how do we do that? Well, with Nodestream, it's actually pretty darn simple. So we'll just take a look again at our Nodestream commands. And we'll see one that looks interesting, Nodestream print schema. Let's see what that does. Because Nodestream, you've basically encoded the schema of your database inside of it, it's able to kind of print it out back for you in a more useful format. And so here's a plain text representation, which is cool, just kind of get a viewing of what's in the database. But again, what I really want is an API schema. So maybe I can export it as GraphQL. So if I do format GraphQL, boom, it spit out a GraphQL schema for you. It's related everything together. And the cool thing is for Neo4j customers and users, this schema is actually directly compatible with the schema that is used by the Neo4j GraphQL library. So you can just kind of straight up copy paste this schema into the Hello World application of a Neo4j GraphQL instance, which is exactly what I've done over here, and start issuing queries against your newly ingested data. So I can run a simple one, like just asking for players' names, and it comes back. Or I can do something more interesting, like this query that queries countries, get what players originated from those countries, and then also get what club those players play for. And boom, it's done that. All these names as part of the schema are all derived from the nodes and relationship types that you've specified in the graph. And it just kind of built out the whole schema for you. That's the main stuff I wanted to show you. I'm going to quickly check in, see if there's any questions in the chat. Let's see. Format types. Can nodestream handle any other data formats, e.g. XML, RDF, JSON? So it handles JSON for sure. All the other types are not explicitly supported, but there's nothing inherent about nodestream that prevents it working from other data types, especially something like XML. You can query into XML. There's nothing inhibiting it. There's just not a product explicit or a component built into the nodestream system for it. So you can do that. I think those are all the questions. Yeah, if you have any other questions. Can you adjust the batching of the data? You absolutely can. Yep. So if you open up a pipeline file, you'll see that there's a batch size argument provided in it. You can adjust this value up. Different sizes are going to work better depending on your data structure, of course. So this is a knob that you can have to tweak. The other thing that we're working on is adding a feature for how it does the batching and giving you a couple different options. If you're familiar with Neo4j, the way it does batching right now is that it does APOC iterate commands in parallel mode. So we're have a couple PRs outstanding for tweaking the way that it does that batching to give you some different knobs to tweak there as well. Let me just check in. Can you build a low-code way to input data? In some ways, that's what this whole framework is about. Because there's all of these different extractors. For instance, let me just kind of show you through a couple of them. There's an extractor for reading from a generic stream with a connector to Kafka. So you can just pull data off of a Kafka topic just by adding in this section here. The same thing for things like Amazon's Athena and S3. You can pull from a remote file as opposed to a local file. There's a simple API extractor if your API is just like sending you JSON and you have to pass like headers and some things like that. So there's all kinds of options. And like I said earlier, you can build your own component. So there's like a base class that you inherit from, and then you can do, as long as you fulfill that interface, you can swap in any data source you want. And then the rest of the pipeline should work just fine. Is nodestream performing merge clauses in the backend if we want to update the data? Yes, it is. If you're relating to things, you can also opt into just matching on something if you only want a relationship to be created if the node's already there. So there's that. Our other graph database is supported. Not currently, there's no other connectors, but the framework is built so that there can be. Particularly languages that use, or databases that use Cypher. That's why this is called the graph database writer. It's not called a Neo4j writer. This database here is what technology you provide. So again, if you want to plug in your own connector to a different database or contribute one back to the project, you absolutely can. it parses everything into an intermediary format and then sort of compiles it as queries to execute against whatever database it needs to. So you can absolutely write some code to get it to connect to a different database. Absolutely, yeah, large files are supported. We pull in, yeah, like Chad's put in the chat, multi-gigabyte files very easily. The way it does that is that everything is primarily streamed to keep stuff out of memory as much as possible. So it tries to commit or just have roughly one batch of stuff in memory. What advantages does this give us? So first is it's just a solution out of the box, and it's developable. So it's designed to be developer friendly. It's designed to be efficient, and it's designed to be consistent so that everything is kind of ingested and updated in the same way. How would you import multiple tables that are linked? So there's a couple of different ways to do that. You can run multiple different pipelines for each one of the tables, and it will just kind of merge stuff together. Or you could do like a SQL join on a couple different tables and just kind of get a flat thing and map things as you see fit. Deleting nodes and relationships, there's no way to do that in the pipeline, but there is a TTL mechanism built into nodestream. That's why it has, one of the reasons why it has timestamps is that you can just run a pipeline that evicts old data as you see fit. I think I caught up on questions.
Neo model versus
Neo model versus Neo model. Yeah, so Neo model is a ORM, ODM, or object graph mapper. Its job is to map data from a database into objects and vice versa. So it's a little bit of a different use case. This is all about just getting data into the graph database. So, yeah. Thank you, everybody, for listening. There's all kinds of stuff on the repo, so if you have more, please feel free to reach out on the GitHub and we'll connect. Thank you, everybody.